Okay, we're making a little bit of a transition today from organic chemistry into biochemistry. And I think the first day of class I pointed out that you really have kind of a unique opportunity here in this course, that you get 8 weeks of organic chemistry and then followed by about 8 weeks of biochemistry. Most chemistry students are maybe taking a year of organic, and they get that all behind them and they put it away, and then they move on to biochemistry. They're taking them as separate courses. Why do I think it's kind of an interesting opportunity? Well, what you're going to start seeing here is we're going to start moving into biologically active molecules. Molecules that are floating around in your body and doing various things. And you're going to see that they are, for the most part, organic molecules. They are carbon-based molecules. That, a couple things. One, they're biologically active. They have some sort of biological purpose and function to them. And number two, they will have multiple functionalities on the same molecule, typically. Very rarely do you see a biologically active molecule that is just like an alkane or even just an alcohol. It's usually got other stuff on there. There's a nitrogen, there might be a sulfur, there's stuff. They're a little bit more creative, sometimes a little bit more complex. Now in organic chemistry, where we went from chapter 10 to 15 and we looked at classes of organic compounds, alkanes, alkenes, alcohols, aldehydes, ketones, etc. In biochemistry, we're going to look at 4 major categories: carbohydrates, lipids, protein, and nucleic acids. Chapter 16 is carbohydrates. Lipids is chapter 17. Chapter 18 and 19 is protein. Amino acids, structure of protein molecules, and enzymes. That's going to be chapter 18 and 19. And then chapter 20 will finish off with nucleic acids. Okay? So that's kind of where we are. And we're segueing into carbohydrates. Today's been kind of a wild day. A lot of weather going on. How many of you got deluged one way, shape, or form? I know Trang did. She's still trying to dry out her shoes, right? Yeah, okay.
Flood area.
Did you?
Yeah, it wasn't fun.
How deep?
Well, luckily, we were about to hit me and my sister, but she got late, so we were trying to get out and go through the big one. And right after we were about to hit the intersection that go onto the highway, it flooded. So we were like, well, our car's a little higher up than most of these other cars, so we can go for it. But so we were deciding if this yellow car and then it just got stuck. And then we're just like, yeah, we'll just reverse our way out of here.
What, the car in front of you got stuck?
So we were just like, that's a bad idea, Jacob. I don't think you should do that. Like, why that? And she points to it because of that, and then like, yep. And the way that the car was.
Was there anybody behind you?
Well, here's the thing. Everybody else saw that, so they were smart enough to already decide, yeah, let's go the other way. But where we were at, there was no way to get to another road. So we actually had to go into the road that the other way. So
How deep was the water?
like from here to there.
Is that right?
Yeah.
Whoa.
Yeah.
But you're here. Okay, and you got a story. Okay, and you're not going to drive through water on the road again? Nope. Okay.
Dangerous.
Yeah, I was in it. I usually get here about 7:15 because I didn't have an 8 o'clock class. I said, oh, I'm going to go in around 10, and I'm driving around 9:30, and I'm thinking, oh, I wish I'd gone in early. It was just
That's the
deluging. Yeah, at 9:30, it looked like night out there, practically. And then I was hoping that it wasn't going to hail, because they said it might hail.
This stuff
Did it? It did hail.
I was like waiting for you to like say classes counseling.
Yeah, I don't have the Canvas app on my phone. I would have probably had a wreck. Should have done that.
We were not good.
I did send a note out to my 11 o'clock class, and I told them, come to the 12:30 class. That's what I didn't cancel class, but I told them, if you're on campus, come at 11. If you're not on campus, then feel free to come to the 12:30 class.
And no one did.
No one did. So I almost killed myself to get that email out. Nobody took it up. All this is being recorded. Okay. For training purposes only, right? Is that what they say? You get on the phone. Your call may be recorded for training purposes only. Okay. All right, back to carbohydrates. Well, I'll tell you what I did do. I gave you, for attendance today, you got 2 checks for being here. Jacob should probably get 3, but don't tell him that. Okay? You each got 2 checks, so if you missed another class, that will make up for it. See that?
Class is gonna be
The NVC students are, I mean, they're determined. If we got a 12:30 class, I'm going to be there. Right?
Yes.
Because I'm going to be there.
11 o'clock.
So if I'm going to be there, you're going to be there. But always drive safely. All right. Carbohydrates. Let's go. Here's what we want to try to learn in this chapter. Know the difference between complex and simple carbohydrates. We're going to talk about mono, di, and poly. I'll just go through this real quickly. There are a couple different functional groups on there. Know how to name a monosaccharide based on the functional group and the number of carbons. We'll go through that. An important part right here, and we'll try to get about this far today, will be understanding what we mean by stereoisomers, or sometimes referred to as optical isomers. And this is really important when you get into biologically active molecules. Many times there's 2 very similar forms of the same molecule, and the biologically active, the living system, rejects one and only uses the other one. And that's the D and L. So for example, you use D-glucose, but your body, if you ingest L-glucose, it's not sweet, and your body just eliminates it. Doesn't use it. Doesn't metabolize L-glucose. Only metabolizes D-glucose. So we want to try to get that far. And then there'll be a few saccharides that I want you to memorize. And then we'll get into Haworth projections. This is where the molecule cyclizes. That'll be Monday. And then these other various things. We'll talk about disaccharides, some different reactions and diseases associated with it, and then we'll look at polysaccharides. So that's where we're headed here. Today I'm going to have you make a glucose molecule, and then we'll keep it till Monday, and you'll do something else with it on Monday. Was there a big long piece of masking tape back here? That's going to be critical. Thank you. I'm going to need that later. That's mine. There we go. Thank you. All right. What do we use carbohydrates for? We burn them. Your body burns them. You don't end up with a flame, but you do produce heat, don't you? Your body right now, it's about 20 degrees centigrade in here, and your body is at 38. 18 degrees hotter than the room. How you do that? You just keep burning calories. Remember, calories? That's an energy term. It's the amount of heat necessary to raise 1 gram of water 1 degree centigrade. And a nutritional calorie is 1,000 of those calories. It's a kilocalorie. All right, so calorie is an energy term. So when you see calories on the back of any label, any food you're eating, it's talking about what is the energy content of this food, because you need energy. You need energy to keep your body 18 degrees higher than room temperature. And carbohydrates is the primary way Fats also are, matter of fact, you can get more energy out of fat than out of carbohydrates. Functional groups, there's 2 of them here. There's going to be lots of OHs. See that? Lots of OHs on these saccharides. And there is going to be a carbonyl, carbon-oxygen double bond. Get used to the fact that when you see a CHO, that's a aldehyde. Remember, that's an aldehyde. That's not a hydroxyl group. That's one of these right there. And then OH is a hydroxyl. So HO, we're talking about an H on the carbon and an oxygen on the carbon. But it's a double bonded oxygen. Later on, or in many cases, you'll see these not in a straight chain, but cyclized. And usually either 6-membered rings or 5-membered rings. And that usually is a oxygen right there. Carbon, 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 and an oxygen. But that is just kind of the symbol used for a glucose, a monosaccharide like glucose. And then if you see 2 of them linked together like that with a bond between them, it's depicting a disaccharide, 2 saccharides. That's a glycosidic bond between there. We'll see what that bond is a little bit more specifically later. Okay, this is just terminology that you should kind of grasp and be a little bit familiar with. So a monosaccharide, disaccharide, an oligo is a prefix here meaning 3 to 10 units long. It's not yet really long enough to be considered a polysaccharide. Poly meaning many. This isn't many, it's 3 to 10. It's not 1, it's not 2, and it's not many. So it's an oligosaccharide. Homopolysaccharides. That would be a polysaccharide, many sugar units, but they're all the same. Glycogen is a polysaccharide made up of glucose. That's how your body stores glucose, as glycogen. And then you can have a heteropolysaccharide. You have more than one different saccharide in there. It could be glucose, fructose, other saccharides that this might be. And then you can see this is linear. This is a linear portion here, but on occasion you can, and this is carbon number 1, 4, so this is a 1,4 link, 1,4 link. Carbon number 1 linked to carbon number 4. But over here at carbon number 2, you could get a branch forming coming off on occasion. Or so you can get branching. Cellulose is a carbohydrate. The trunk of an oak tree out there, cellulose. And it's got a lot of cross-linking on it. Imagine how strong that is. Question? Yeah, we can't digest cellulose. Cows can, but we can't. But you do need fiber. So chew on oak branches. You get some fiber. You want fiber. What's fiber? Stuff that goes through your digestive system, but you can't digest it. But you need it. It really helps your digestive system. What was I going to say about the oak? Imagine those oak trees out there. You go see these oak trees with these massive limbs coming off, leaning off like this. They hold them out there for 24 hours a day, 7 days a week. It's cellulose. It's a carbohydrate. Pretty strong stuff, right? That's what it is. It's a carbohydrate. Cross-linked, engineering-wise, in terms of its strength, and it's incredible. You can go sit on the branch for 24 hours, and the oak tree just holds you up. So this is pretty strong stuff. All right, naming. Wrap your mind around this. The two things you want to keep in mind. Where is the carbonyl? Where is the carbonyl group? If it's right at the top, it's an aldehyde. Okay, you can see we're talking about organic molecules here, right? But they're biologically active organic molecules. An aldehyde, there's an aldehyde. Now over here we get to something else. It's got a carbonyl. And that's typically where you would find it. What is that? That's not an aldehyde. What is that? It's a ketone. All right? So when we go into biochemistry, we call that is an aldose. It's an aldehyde functional ose. OSE ending referring to saccharides. All right? So a lot of times, glucose, fructose, sucrose, lactose, maltose, it's telling you, I think this is a saccharide. The OSE ending. So this is an aldose. This is an aldose. Now what's different about them? The number of carbons. 1, 2, 3 carbons. It's a triose. So this is two things simultaneously. Just like you can be a brother and a son, and you're the same person. This is a aldose, and it is a triose, or we would call it an aldotriose. Those are all just categories it fits into. That's not its name. Its name is D-glyceraldehyde. That is D-glyceraldehyde. All right, here, this is an aldose. It is an hexose, 6 carbons long. It's an aldohexose, but that particular molecule, and it's going to be right, left, right. We're going to have a hydroxyl on the right, the left, and the right. That's D-glucose. If it was right, it's something else. It's a different sugar. So that's D-glucose. Now this also has 6 carbons, so it's a hexose, but it's a ketose, and it is a ketohexose, and that's fructose. And it's right, left, just like glucose, right, left, but then when you get up to that carbon, instead of being an OH there, it's a carbonyl right there. And then you got a CH2OH at the top. You got one at the top and one at the bottom. What did I want to say? Okay, even when you do see ketoses, they're usually on that, which is carbon number 2. They don't just show up anywhere. They typically always, it's either an aldose or it's a carbonyl on the second carbon, a ketose. Yeah, and that's D-fructose. Here's my little, what do I do with the pen?
Is it the black one?
No, I need the one that runs this thing. Ah, thank you. Same color. Okay. Ah, what's this all about? I always use that slide when it's been a really bad weather day. Okay. What's that about? What's this about? And what is, this is for a bad hair day. That's for a bad weather day. Okay, now, pay attention. You guys are budding scientists, and what do scientists do? They pay careful attention and they observe minor details. So what do I got here? I've got a carbon. You can imagine that's a carbon. If you want to say Okay, that's an oxygen and a hydrogen. Oxygen and hydrogen. And what else? Something else. But I've got a carbon here with 4 different things on it. Yes?
Yes.
And I've got a carbon here with 4 different things on it. These 4 different things are the same 4 things that are on this carbon. So are these 2 molecules identical?
Are they in different positions?
Yes? Are they identical? You're already a little suspicious of that. I think it's a trick question, don't you?
Yes.
It is. Let me put the yellow one up top there.
Yes.
You think they're identical?
Wait, let me
Okay, let me ask you this question.
No, they're not identical because the green are flipped.
Okay. What would be the test that we can say whether these are identical or not identical?
Don't you have to like put them on top of each other?
Put them on top of each other or superimpose them on one another.
See?
So I'm going to get this yellow one at the top. I got the red one where the red one is. And I'm going to drop the red one onto the red one. I've got the yellow one on the yellow one. Uh-oh. The green one is on the white one, and the white one is on the green one.
So you did not. They're not the same.
So they're not the same. These are not identical. But I'll tell you what they are. Let's put this up here. Train, put your head down. All right. Okay, let's see. I got the red pointing towards you. I got the red pointing towards me. I got the green over here and the white over there and the yellow there. Now look at the mirror. Look at the image of that in the mirror. And look at this. Are those the same?
They're. Yeah.
This molecule here is the mirror image of this molecule. They are mirror images of each other. I mean, I look at them like right then, and boy, they look pretty identical. But I go to try to drop them on top of each other, and they're not. All right, I'm not doing anything. I haven't moved anything. Right? So they're not identical, but they are mirror images of one another. So what about the hands? Right hand? You got a right hand and a left hand? They are not identical. Your right hand is not identical. It is not superimposable on your left hand. It is the mirror image of your left hand. You follow me?
Yes.
So they are mirror images of one another. And it's really great that they're that way, because then you can play baseball. You see, you can grab a nice club, play baseball, whatever. You can do a whole lot of things with 2 hands that complement one another like this, but they're not identical. They're complementary. All right. So this gives rise to a new kind of isomer, you would think it gets the name optical isomer from this, but it actually gets the name optical isomer for another reason. I'll show you in a minute. Okay, it does look like optically, this is a mirror image of that. So they're kind of optically identical, although they are different. The structure is a little bit different. The structure really isn't different, but they have 4 different things on them. That is going to be the thing that gives rise to optical isomers, or what we call stereo isomers, is a carbon that has 4 different things on it. They all have to be different. 4 things on that carbon all have to be different, and you're going to get stereo isomers. Okay? So, yeah, I want you to appreciate this, because we're going to be looking at D-glucose and see exactly what it is. Now, we're going over to glyceraldehyde. So where's my glyceraldehyde? Right here. Get a different oxygen on here. see if I have two. Here's a glyceraldehyde. It needs one more hydrogen right here. So there's a CH2OH group down here. Here's a carbon with a hydroxyl and a hydrogen, and here's a carbonyl. Here's another one. So I have, this is the simplest glucose, glyceraldehyde, not the simplest glucose. The simplest saccharide, glyceraldehyde. 3 carbons. So it's got 3 carbons. Here's another one. Now, are these the same? If I get these in kind of a similar orientation, I've got the aldehyde at the top, I've got the carbons going vertically down, and I bring this over, and can you see I can't superimpose this on there? Look at this. Look at this carbon right here. This has got the hydroxyl on the right, and this has the hydroxyl on the left. So these are 2 different molecules. Yes? You follow that? They look very, very similar, except for the fact that this hydroxyl is here, not there. This hydroxyl is here, not there. So if I go to superimpose it, everything can superimpose. This can float around, and I can get those hydrogens and everything. This can rotate, but there isn't any way to rotate this. If I turned it around like that, I could get them on top of each other. But now the carbonyl is down here. You see? So if I keep it in that orientation, so that this will fit to there, and this will fit down there, this is what's different, right in the center. This happens to be L-glyceraldehyde, and this is D-glyceraldehyde. L, this is on the left, and D, this is on the right. Now the reason that's not an R is we're using German here. Levo-rotated and dextro-rotated, dextro-rotatory. And I don't know very much German. That's about it right there. It's all my German. Okay? But that's what we're talking about. And well, I'll tell you why they talk about rotation in a minute. So it gives rise to these all right, so this gives rise to 2 isomers. Glyceraldehyde consists of 2 isomers. Spatial arrangement of these atoms are mirror images. They're enantiomers. When 2 compounds have the same molecular and structural formulas but cannot be superimposed on each other, the compounds are said to be chiral. They will contain a chiral carbon with 4 different things on it. That's a chiral carbon. And any molecule containing a chiral carbon can exist as a pair of enantiomers. So if I showed you that molecule, and I said, well, let's look at that carbon. It has one thing here. It has an OH over here, hydrogen OH. It has this thing up here, which is different from this thing down here. When I say thing, this whole complex at the bottom is different from this. So that carbon has 1, 2, 3, 4 different things on it. So even if I'm just showing you one molecule, and you say, oh, there's a chiral carbon, you would say there is another molecule that is the mirror image of this. There's another isomer that would make up a pair of enantiomers. So that's what this is. These 2 here represent a pair of enantiomers. Now we're making a big deal out of glyceraldehyde because you're going to see it's going to always pop up. This is going to be our reference molecule to tell whether something is D or L. Anything else, we're going to come back and relate it to this L-glyceraldehyde, this D-glyceraldehyde. And we're going to say if it's like this one, it's D. If it's like this one, it's L. We're going to even do that with amino acids. We're going to come back and look at glyceraldehydes to see whether they're D or L amino acids. So this is our gold standard. These molecules here are going to be our reference molecules. Okay, so let me just go over that. So here's what we're looking at. Here's our glyceraldehyde. There's our glyceraldehyde. Now, we're looking for a chiral carbon. What is a chiral carbon? It's a carbon that has 4 different things on it. Is this chiral? Is that carbon a chiral carbon? Yes? No?
And there's 4 different things on the ring.
4 different.
Oh no, well, 2 of them.
2 of them are the same. It has 1, 2, 3, 4 things on it. Yes, that carbon has 4 things on it. But because those 2 hydrogens are the same, it's not a chiral carbon. That's not a chiral center. How about that carbon? No, why no? How many things does it have on it? 3. Has only 3 things. A hydrogen, an oxygen, and this thing. This is the other thing. So it only has 3, so that's not chiral. But let's look at that. We've got a hydrogen. We have a hydroxyl. Those are different. We have a CH2 OH group. That's what this is. The CH2OH group on the bottom. And we have this aldehyde at the top. You can see that is different from this and different from those 2. So we got 4 different things. So I'm going to tag that as a chiral carbon, which I've been showing you. So that means there is also this molecule. Yeah, this one is L.
And that one's
This is L-glyceraldehyde, and this is D. The hydroxyl is on the left, so L goes with left. D goes with it being on the right. So if you keep L straight, you'll know what D means. All right, this slide here just makes the point, simply, I hope, that if we started going from glyceraldehyde, which has only 3 carbons, so if we move from just 3 carbons to 4 carbons, here's erythrose, we could start examining each one of these carbons. We look at that one, it only has 3 things on it. No. This one has 2 hydrogens and an OH. And that other thing, no, that's not chiral. But if we look at this one, we have, we've got a hydrogen, an OH, we've got a CH2OH, and we have this. 4 things on it. So that's a chiral carbon. Then if you moved up to here, you'd have 1, 2, 3, and this whole big thing down here, which is different from that. So that is chiral. So erythrose actually has 2 chiral centers. And so if you went to 5 carbons, it would get more complicated. You get to 6 glucose, it gets more complicated. No, these 2 are not chiral. But if you walked on up here, you would see that it's got 4 chiral carbons. And this is the biologically active molecule right here. And the L-glucose is not. So this is showing you the capability of living systems to distinguish. If I took these molecules, if I took these two molecules into the laboratory, I would find the same solubilities in water and any other solvent you want to look at. The same kind of reactivity with Benedict's reagent. Same ability to be oxidized to, this would be glucon, the carboxylic acid version of these. All of these would react the same. DNL in the laboratory I wouldn't notice any difference. I'll show you the only thing I would notice. So I wouldn't notice any difference in reactivity, and yet the body will take one of those and use it and completely ignore the other one. And it's going to carry through reactions. But here's the thing that, here's where the optical activity comes from. This is the only way I could tell D-glyceraldehyde from L-glyceraldehyde in the laboratory, would be to put it in a polarimeter, a simple little device. These are not very expensive. You basically got a light bulb here. It's shining light through. You have a polarized filter like you would have on polarized glasses. And what does that do? The light here, the wavelengths of the light are oriented in all different kinds of orientations. The whole 360-degree angle here. There's light. It passes through the polarized filter, and the wavelength, only one orientation comes through the filter. Then you put your sample right here. You have some sort of a container with your sample in it. You shift it down in there, and this polarized light passes through your sample, and it rotates the polarized light. You have a detector over here that says, okay, it's coming up at a 180-degree orientation, and you put your sample in there and it goes, whoop, it shifted 15 degrees to the right or 15 degrees to the left. A mixture of these two, 50-50 mixture of these two, the polarized light would just kind of, half of it be getting rotated one way and the other way, and it would come back through the same way. But if I had pure D-glucose or D-glyceraldehyde, it would shift it to one direction or the other. So that's what we mean by levo-rotated or dextro-rotated. I forget who discovered this, but someone happened to discover that this is what made a difference. The direction of rotating polarized light. Okay, we'll get into Fisher rotations on Monday. Just to show you, here are Fisher projections. Excuse me, Fisher projection. But to just show you what that is kind of talking about, let's take the D, which is the right one. What we're doing with that, and Fisher said, okay, how do I tell someone which isomer I'm talking about? So he said, what we need to do is we need to establish a very prescribed way of holding and drawing these molecules. And if everybody draws them in this prescribed way, we'll know what molecule we're talking about. What is that prescribed way? Number one, you put the carbon-oxygen double bond to the top. You put the carbon backbone of the saccharide vertical. So one, next thing, vertical. Number three, have the carbon backbone fading away from you. It's vertical and fading away from you. Have the OH and the hydroxide, the OH and the hydrogen horizontal and pointing towards you. Okay? You with me? Then you say, okay, what side is that on? That's on the right. That's D-glucose, D-glyceraldehyde. You follow me? You got to do all those things. You can't turn it upside down. See, if I turn it upside down, all of a sudden that shows up on the left, right? So you can't do that. We have to say, okay, that has to be at the top. This has to be down. The carbons have to, if I turned it around like this, and the carbons coming towards you, all of a sudden that's on the right. All of that doesn't work. It's got to be these prescribed way. And then what Fisher said is take that molecule now and flatten it on a two-dimensional piece of paper, and you draw it, and that's your Fisher projection. So squish it down there right there, and you've got, there's your chiral carbon, and I've got an OH here, I've got a hydrogen here, so that's what Fisher would do. He would say, okay, get it in that orientation, squish it down into a two-dimensional array, and draw it. And there you've got OH on the right, this is D-glyceraldehyde. Okay? And this is a little probably complicated and unusual, so I'll introduce it right now. On Monday we'll start there. We'll come back to this, looking at these projections. But I'll tell you what I want you to do. Break up into threes and fours if you want to stick with your team that's presenting on Wednesday. That'd be fine. Get into those teams. And what I want everybody to do right now is, what do I want you to do right now? I want you to make, this is D-glucose. And that's all you got to do today. You make this, and these are going to be black, these are going to be red, and these are going to be white. And use the stiff bonds for everything except that double bond right there. So use this for the carbon-oxygen double bond, and then use the stiff ones for the others. Some of these aren't going to have a lot of carbons. So get into your teams. You just make a glucose. I'll give you a little piece of masking tape and put your initials on it. You may or may not find enough carbons in your box. If you don't, we'll open up a bunch up front. If you run out of the bonds you need, or kind of bonds, beads you need, here's plenty of little beads. That's a good one.
I don't know which one this one belongs to. That's actually.
Get my stuff away.
There you go. That's good. Here's there.
So black and red. Which one I got?
One card? Or no, they're not. Right.
They're just not being shown. That's 6 carbons. 1, 2, 3, 4, 5, 6. Yeah.
Okay, make sure we're going to keep these, because on Monday we're going to do a little bit more with them. Okay? So we're just kind of getting our glucose so we can work with it some more on Monday.
I'm sorry, the top.
Here's something.
How do you get the H on there? Oh, hello.
The red is the O. This is the 108. Red is 08. So here.
And then we just start.
Okay, this is an 08. Let me see the second carbon. Right there.
Yeah, that's what I was trying to figure out.
Go right here.
Straight this way. Yeah.
Oh, it connects with
Yeah, we need 3 of those. Actually, 4. Well, there's 4 because there's one that's HO. But what's your husband's name? Casey.
Oh, that's just, I was like, that's her name. Yeah.
Oh, yeah, they are. Oh, yeah, my
Where are we? Oh, H.
The second one. Like this.
No, you're right.
Oh, H.
Turn it that way. Yeah, that's right. And then now you have to put the OH over here. This one. How do we connect the OH?
This is okay. We still need attachments on this side. Yeah.
You have 6 carbons? Yeah, 6 carbons.
H. Oh, H. And then B. Oh, H. It'll be H. Actually,
Remember the part of the
There goes the way.